Imagine a programming project you've just wrapped up.
Right?
Maybe it's a microservice for your company's backend, or, I don't know, an open source contribution,
Yeah.
or even just a really complex data parsing script you've been optimizing all week.
Yeah, we've all been there.
Exactly. So you run the build command, the compiler throws 0 warnings, and the architecture looks solid. You feel good.
Of course you do. It compiles.
But compiling is really just the baseline, isn't it? How do you rigorously mathematically prove that this system actually meets its functional objectives out in the wild?
You generally can't.
Right. I mean, you certainly can't simulate every single concurrent user or every corrupted data packet that might hit your server. And what happens when your project relies heavily on third-party dependencies?
Where you don't even control the source code.
Exactly. You can't even see the code.
And that right there is the defining bottleneck of software engineering, because writing the logic is honestly often the most straightforward part of the entire process.
The fun part.
Right, the fun part. The true complexity arises when you have to systematically prove that your logic holds up under conditions you couldn't fully anticipate. The transition from a compiled build to a production-ready system is it's a rigorous, often unforgiving filter.
And that filter is what we are focusing on today. Welcome to this deep dive. Today, we have a highly analytical framework to explore with you.
It's a fascinating one.
It really is. We are pulling insights from Chapter 1 of a software testing guide published by the Open University of Israel. Our mission today is to shortcut your path to mastering the hidden architecture of software testing.
Bypassing the basic jargon.
Bypassing the jargon entirely. We want to look at the structural philosophy of fault detection. How do developers and QA architects actually ensure complex systems remain operational?
Because testing is a fundamentally different discipline from programming. It requires a distinct cognitive approach.
A completely different mindset.
Exactly. It's a philosophy of problem-saving, risk mitigation, and quality assurance that treats code not as a finished product, but as a hypothesis that must be aggressively challenged.
I love that framing. And when you grasp the architecture of this validation process, you really gain a much clearer picture of how our fragile digital infrastructure is actually maintained.
Very fragile.
So true. Let's get right into the foundational taxonomy. I want to start with a crucial distinction between two concepts that are, frankly, frequently conflated in Agile stand-ups.
Oh, constantly. Verification and validation.
Yes. Verification and validation. Let's break that down because they sound like synonyms, but they aren't.
That distinction dictates the entire direction of a QA cycle. Verification is a strictly internal, highly technical evaluation.
It's checking the math.
Basically, yeah.
Yeah.
It is the process of confirming whether the software architecture and implementation meet the specified technical requirements. You're evaluating the code against the blueprint.
So if the spec document says a function must return a 64-bit integer, and it does, that component passes verification.
Exactly. It does what the internal documents say it should do.
Invalidation operates on a completely different axis. Validation is evaluating whether the final product actually fulfills the client's operational needs and expectations.
Right. Verification asks, did we build the system right?
While validation asks, did we build the right system?
Precisely. And you can routinely encounter scenarios where a system flawlessly passes verification, but catastrophically fails validation.
Oh, I've seen that happen. A development team executes this perfect implementation of a feature based on a heavily documented spec. They achieve 100% verification.
But if that spec was based on a fundamental misunderstanding of the user's workflow,
The product fails validation entirely. It perfectly executes a totally useless task.
which is incredibly costly.
It is. But that misalignment brings us to a more granular level of failure. The source material outlines a very specific chain reaction here, a taxonomy of a system breakdown.
From the ground up.
Right. It starts at the absolute lowest level with a system defect, or what they call a fault.
And what's fascinating here is the temporal separation between the stages of a breakdown. A fault is a static defect in the code itself.
Like a logic error.
A logic error, an unhandled exception, an incorrect algorithmic step. But a fault doesn't immediately break the system. A fault only becomes active when the specific control flow executes that flawed line of code.
Which then transitions the system into an error state.
Exactly.
And an error state means the system's internal variables, its memory footprint, are now corrupted.
Yeah.
They are operating outside of the design parameters.
But even an error state doesn't necessarily mean the user sees a crash right away.
Right, and that is terrifying.
It's precisely the opposite of what people assume, which is what makes debugging complex systems so notoriously difficult. A system can operate in an error state for hours or even days.
Think of a subtle memory leak. The fault is the unreleased memory allocation in the code. The error state is the gradually increasing RAM consumption behind the scenes. The system is compromised, but it's still functioning.
It is only when the system runs entirely out of memory and the operating system violently kills the process that you experience the third and final stage.
The system failure.
The failure. The fault creates the error, and the unresolved error eventually triggers the failure.
So what does this all mean?
Well,
From a structural standpoint, preventing that domino effect requires a profound psychological shift in how teams approach the code base.
it really does. There is a fundamental clashing of mindsets between the developer writing the software and the tester evaluating it.
The psychological divergence there is one of the most significant hurdles in software engineering.
Absolutely. Because when a programmer tests their own code, they are inherently operating under confirmation bias.
They design the logic.
They designed it, so they inherently understand the happy path, the inputs that should result in a successful execution. They run tests to confirm that their mental model was successfully translated into syntax.
They're looking for a green build. They want the deployment to succeed. It's human nature.
But a dedicated tester operates with a destructive mandate. Their explicit objective is to search for and isolate faults.
They want it to break.
They are not running tests to prove the software works. They are engineering edge cases, boundary conditions, unexpected concurrent loads.
All specifically designed to force the system into an error state.
Yes, it's the difference between building a cryptographic algorithm and paying a team of penetration testers to actively try and break your encryption.
And cultivating that adversarial mindset is a vital risk management strategy. We deploy critical resources to find these faults early.
Because the cost of remediation scales exponentially.
Right. Finding and fixing a logic fault during the unit testing phase costs a fraction of the resources required to patch a live system later.
Imagine having to migrate corrupted database records and manage the fallout of a system failure in production. It's a nightmare.
A total nightmare. So understanding that mandate sets the stage for how we actually execute these evaluations, the fundamental atomic unit of this entire process is the test case.
The building block.
Exactly. At its core, a test case is simply a mathematical pair.
The architecture of a test case relies on two discrete components. You have the input state provided to the system and the expected outcome resulting from that specific input.
Mathematically, we denote this as input, comma, expected output.
Right.
And that output depends heavily on the architecture of the system.
Yeah.
I mean, for a pure stateless function, the outcome is just the return value.
Simple enough.
But for complex state-based systems like a database transaction or a user session, the expected outcome includes the transition of the system's internal state, not just what is rendered on the screen.
The critical dependency in that pairing is the expected outcome. A test execution without a predefined expected outcome is operationally useless.
You can't just guess.
No. You can feed a massive data set into an undocumented API and log the responses, sure, but without knowing exactly what the API was supposed to return, you are merely observing behavior.
You cannot evaluate success or failure. You have no baseline.
None at all.
Here's where it gets really interesting. How do we establish that baseline when the system is too complex for a developer to simply calculate the expected output in their head?
We rely on a concept known as the oracle.
The oracle. It sounds mystical.
It does, but it's a vital construct in testing theory. It represents the trusted, independent entity that provides the expected outcome for a given input.
Because a compiled software can only demonstrate its actual behavior, we need an external source of truth to validate against.
Precisely. And the oracle takes many forms depending on the domain. It could be a human subject matter expert.
So if you are developing algorithmic trading software, your oracle isn't a senior developer.
No, it's a quantitative analyst who can definitively say, given these specific market inputs, the risk exposure matrix should look exactly like this.
Human oracles are common for complex business logic, but they don't scale well for automated continuous integration pipelines, do they?
Not at all. You can't have a human manually verifying thousands of builds a day. In automated environments, the oracle might be a pre-calculated knowledge base, a deterministic mathematical model, or even a legacy system.
Oh, using a legacy system as an oracle. That introduces a fascinating dynamic. You feed identical inputs into the old trusted monolith and the new refactored microservice.
And you assert that the outputs match perfectly.
That technique is incredibly powerful for massive system migrations, but it also carries inherent risk, right?
Huge risk. If you use a legacy system as your oracle, you are implicitly trusting that the legacy system's behavior is flawless.
Which it rarely is.
Exactly. If the legacy codebase contains undocumented quirks or long-standing hidden faults, your new system will be rigorously tested to replicate those exact same faults.
The integrity of your entire QA process is entirely dependent on the integrity of your oracle.
It's a single point of failure in your testing logic.
So, assuming we have a reliable oracle, we then scale these test cases across the development lifecycle. This brings us to the V model of software development and testing.
The V model.
It structures the QA process from microscopic code blocks all the way up to the macro-level architecture.
It creates a synchronous relationship between the phases of development and the phases of testing. You start at the base level with unit testing.
That's the micro-level.
Yes. Here, you are isolating the smallest testable parts of an application, individual functions, methods, or classes. You mock out any external dependencies, databases, or network calls.
You replace them with fake versions just for the test.
Right. And you evaluate the control flow of that specific block of code in complete isolation.
By mocking those dependencies, you ensure that if the unit test fails, the fault is definitively located within that specific block of code, not in some external database connection.
Which saves countless hours of debugging.
But isolation only gets you so far. Once those units are verified, the V model dictates a move to integration testing.
Integration testing is where the architecture truly gets stress tested. You are taking those isolated, verified units and combining them to test the interfaces and data flow between them.
Because a component might perfectly manage its internal state, but if it serializes data into a JSON format that the receiving component isn't configured to parse,
the system crashes. Integration testing focuses on the contracts and communication boundaries between modules.
And finally, we zoom out to system testing,
where the application is deployed as a fully integrated entity in an environment that mirrors production.
This is where you evaluate the non-functional requirements: load balancing, concurrent user stress, memory limits, end-to-end user workflows.
The whole package. But the life cycle of software is continuous. You don't just build it once and abandon it.
You refactor code, you optimize queries, you patch security vulnerabilities.
Which necessitates regression testing.
Regression testing is the safety net. Whenever a module is modified, you run your regression suite to ensure that your localized patch didn't create a cascading failure somewhere else in the architecture.
The butterfly effect in complex code bases is a very real, well-documented phenomenon. You optimize a database index to speed up the authentication service.
And suddenly, the reporting dashboard times out.
Because it secretly relied on the old indexing latency to resolve a race condition. Regression testing focuses specifically on verifying that changes have not degraded previously validated functionality.
But running a massive regression suite on every single commit is computationally expensive.
Extremely. Which forces teams to be highly strategic about test selection.
And that strategic selection becomes even more complex when we consider the limits of our visibility. Think back to our initial scenario at the start of the deep dive.
The external libraries.
Yes, your project heavily utilizes an open source library or a proprietary third-party API. You don't have access to the source code. How do you test a system when parts of it are completely opaque?
This brings us to the dichotomy of white box versus black box testing methodologies.
Two completely different approaches.
And this division dictates your entire approach to test case design. White box testing, or structural testing, assumes you have complete, unrestricted access to the source code.
You can see the internal logic.
You can see the variable assignments, every nested conditional statement.
Because you have the source code, your testing strategy revolves around evaluating the internal control flow. You are aiming for high branch coverage or path coverage.
Making sure your inputs force the execution of every if, else, and switch statement in the module. You are actively navigating the cyclomatic complexity of the code.
But calculating the exact inputs required to traverse every possible logical path in a massive enterprise application is computationally unfeasible.
It is. Therefore, white box testing is highly effective, but practically limited to the micro level. Unit testing individual functions or small, critical modules.
Which means as we move up the V model to integration and system testing, we have to transition to black box testing.
In black box testing, or functionality testing, the internal logic is hidden from you.
It's literally a black box.
Exactly. You have an abstract model of the system's requirements and the interface specifications. You treat the module as an opaque machine.
You seed at the input, and you evaluate the expected output against the oracle, without any insight into the algorithmic steps the machine took to generate that output.
And this is how we manage the complexity of third-party dependencies. When you use a cryptographic library, you don't perform white box testing on its internal prime number generation.
You perform black box testing. You provide a payload, request encryption, and verify the cipher matches the expected protocol.
You rely on techniques like equivalence partitioning and boundary value analysis to infer the module's stability based solely on its external behavior.
Okay, let's unpack this. We have white box techniques for the granular logic. We have black box techniques for the system boundaries. We have human and automated oracles and a full V-model architecture.
A very robust framework.
But this all leads to the most persistent, agonizing question for any QA architect.
When is it enough?
Yes. At what point do you stop? How do you mathematically justify that you have run enough tests to consider the release candidate fault-free?
You are touching on the concept of adequate testing. In a continuous deployment environment, you can't delay a release indefinitely to write more test cases.
You have to quantify the effectiveness of your test suite.
You need a metric that proves your tests are actually capable of catching faults.
And one of the most rigorously analytical ways to measure that adequacy is a technique called mutation testing.
It is brilliant.
It really is. We aren't just testing the application anymore. We are dynamically testing the test suite itself.
Which raises an important question. How confident are you that a passing test suite means the code is correct versus the test simply being poorly written?
Right. A bad test will always pass.
Exactly. Mutation testing answers this by deliberately sabotaging the code base.
You utilize an automated tool to introduce thousands of tiny, specific faults into a copy of your application.
These are the mutants.
The mutants. You might invert a Boolean condition, swap an addition operator for subtraction, or change a strictly greater than sign to greater than or equal to.
You engineer these logic bombs, and then you execute your existing test suite against this mutated, broken code base.
The objective is to see if your tests fail. Because if a test fails, it means it successfully detected the mutant. The mutant is killed.
But if your test suite passes and returns a green build despite the presence of the mutant, it means your tests are blind to that specific logical pathway.
The mutant survived.
And by calculating the ratio of killed mutants to total generated mutants, you generate a highly objective mutation score. It's a ruthless evaluation of your test coverage.
But the computational overhead of mutation testing is staggering, isn't it?
Oh, it's massive. If your application has a 5,000 unit tests and the mutation engine generates 2,000 localized mutants,
You potentially have to execute that entire 5,000 test suite 2,000 individual times.
the processing cost is astronomical, which is why it's often reserved for mission-critical components where failure is unacceptable.
Aerospace control systems.
Financial ledgers, medical devices.
But even if you achieve a perfect mutation score on your critical modules, we still have to confront an inescapable mathematical limitation.
If we connect this to the bigger picture, the foundational truth of software engineering is that complete, exhaustive testing is a mathematical impossibility.
It's a hard pill to swallow, but it is entirely impossible.
The primary limitation is the sheer scale of the input domains.
Consider a simple system that accepts just 3 32-bit integer inputs.
To achieve complete coverage, you would need to test every single possible combination of those 3 integers.
And the permutation space for just that is so massive that executing those tests would take decades of continuous compute time.
For 3 integers,
And modern applications process dynamic data streams, asynchronous network events, concurrent user state mutations, hardware-level interrupts.
the state space isn't just massive. For all practical intents and purposes, it is infinite.
Because you cannot exhaust the input domain, software testing is never an exercise in achieving absolute certainty.
No, it is an advanced exercise in risk optimization. The architecture of QA is about strategically selecting a finite subset of test cases that provide the maximum possible coverage of the highest risk execution paths.
You are deploying resources to shrink the margin of error to an acceptable tolerance.
But you can never reduce it to 0.
Never. And realizing that completely shifts your perspective on the digital infrastructure we interact with daily. From the routing protocols that deliver your data packets, to the biometric security on your devices, to the payment gateways processing your transactions.
None of it has been exhaustively tested for every conceivable edge case.
because doing so breaks the laws of computation. Understanding this hidden architecture, the latency between a fault and a failure, the psychological necessity of the destructive tester, the reliance on an independent oracle, and the strategic limits of black box evaluation. It elevates how you analyze system reliability,
You stop asking if a platform is bug-free.
and you start asking if its failure domains are adequately mitigated. That's what you walk away with.
And that architectural reality leaves you with a rather provocative final thought. The source material establishes that because input domains are infinite, complete coverage is a myth.
Right.
Furthermore, modern development heavily relies on black box external dependencies where we cannot audit the structural control flow. We only evaluate the boundaries.
We just see the inputs and outputs.
Exactly. So if the global digital economy is entirely built on an interconnected web of infinitely complex state machines leaning heavily on opaque black box components, isn't every interaction with software essentially a calculated leap of faith? Every time a transaction clears or a system scales, we are fundamentally trusting that somewhere in the pipeline, an oracle successfully predicted the exact right finite subset of inputs to evaluate.